conducting the workshop, who are shown here in this rectangle. And I would also like to thank people who have been truly instrumental to the development of this code. One of them is Jinjian Zhu, who is a former postdoc in the group and is now a professor at Beijing Tech. And also a former postdoc, Ivan Malyev, who's led the development of several parts of the code, as well as another postdoc, Tommaso Chiarotti, who will not be here today. And finally, I also need to thank a long list of former group members. Some of them are listed here, and they're currently postdocs or faculty, or they work in industry, but they're given very important contributions to the code. Now, my pointer is not moving, so that's less than ideal, but I think we will just continue. Okay, so first of all, I hope that people had a chance to download the workshop materials, and you will find both the slides as well as the files to actually run the tutorials. And before getting into the technical details, I wanted to give an overview for the plan for the next 2 days. So after this talk, day one, starting at 10, there will be 2 theory talks, including background material, both on DFT, linear response, DFT, and how to start the calculations, as well as on transport. And then the second half of the day, after the lunch break, which will start at noon Pacific time, we will have 2 practice sessions. One of them on installing the code, compiling it, including with GPUs, as well as post-processing the data from the calculations. The second one will be on setting up the initial repository of data that one needs to then conduct the calculations. And then the final talk for today is going to be on transport calculations, which is probably still one of the main drivers for people who are attracted to our code. So please try to stay until the end today. Tomorrow, we will have talks that combine both theory and practice. The first one, which will start at 9 a.m., so same time as today, will be on non-equilibrium / ultra-fast dynamics. And then on day 2, we will start talking about more advanced and more recent features that have been added to the code. One of them is spin relaxation and spin orbit coupling. And then after the lunch break, we'll continue with advanced topics, including enharmonic phonons and electronic correlations in the framework of density functional theory with the Hubbard U correction. So finally, just to highlight some of the recent developments, as well as features that you may find in future versions of the code, there will be some short talks. So like a sequence of 5, 10-minute talks, just to give you a flavor of, the actual work that we're doing right now, some of which will end in future versions of the code. Okay, so at its heart, Perturbo is a code to model electronic interactions and dynamics in materials. And it obviously uses the first principles formalism, where the structure of the material is the only input, and the goal is to compute these quantities with quantitative accuracy using quantum mechanics combined with advanced numerical algorithms. So the workhorse in this field is density functional theory, and that's basically the starting point to compute the ground state, and bonding in the materials, and kind of find stable structures and ground state properties. But Perturbo builds on top of density functional theory to study electronic interactions using the language of many-body theory. So in this workshop, we will focus primarily on the interactions between electron and atomic vibrations, aka phonons. And we will also talk about the interactions between the electron spin and phonons. But we work on a broader range of phenomena that also include interactions with defects, magnons, excitons, and other quasiparticles and excitations in materials. So then, starting from these accurate interactions, Perturbo does mostly two main tasks. One of them is related to studying transport phenomena, particularly electronic transport. And that also includes studying spin dynamics. And the second one is actually studying phenomena at ultra-fast timescales in the time domain, which I've summarized here as non-equilibrium physics. So I will talk about this physics momentarily during this talk. And first, I wanted to give an overview of Perturbo as a project. So it's an open source code that we have first released in 2021. That was version 1. Now we are at version 3, which has been released earlier this year. And so over the last few years, the project and the number of users have grown significantly at a constant and, in fact, increasing rate to the point that now we basically have a fairly large community of over 1,000 users that are using the code. And that also tracks with both the number of citations as well as papers that are using the code. So just to give an overview of things that the code can do, in terms of electronic interactions, one can compute electron-phonon interactions, spin-phonon interactions, as well as interactions with defects. And this can be done for simple up to fairly complex systems with about up to 100 atoms in the unit cell. The main limiting step is what one can do in density functional theory and linear response density functional theory, and not so much with Perturbo per se. In terms of transport, we have a wide range of features that range from computing conductivities and mobilities to more advanced workflows that involved transport in magnetic fields or spin relaxations, as well as strong electron-phonon coupling and polarons. We will talk about ultra-fast dynamics, where primarily the current version of the code can model the non-equilibrium electronic dynamics in response to a pulse, and as well as model the electron dynamics under an applied electric field. These calculations can now be done in a wide range of systems. Besides, simple materials, we can also model materials with magnetism, spin-orbit coupling, and harmonic phonons, as well as electronic correlations treated within DFT plus U. And so the code is interfaced with one of the most recent versions of Quantum Espresso. Whenever there's a change in Quantum Espresso, we try to update the code to be consistent with that. And over the last few years, we have developed a wide range of tutorials. We have expanded the manual, and we've also made the executable for Perturbo available on supercomputing platforms such as NERSC. So I think that one of the reasons why the code has been so successful is that it's very user-friendly, but it's also modular, so that, for example, it's easy for somebody to add a new piece of physics without knowing the entire code. And finally, the code is fast. It basically performs very efficiently because it's parallelized with both MPI and OpenMP. And starting with version 3, we also have GPU acceleration. So it's basically been designed with the modern tools of software engineering. And you can see here, in fact, that you can use it in a supercomputer, and up to about 1 million code, you still obtain nearly ideal speed up. So if you want to learn more, you can look at the website and the paper, but also over the next 2 days, you will see a wide range of features from the Perturbo-code discussed. And if you have questions, we have a user forum, which is where actually users are quite active. And so that's also a good place to talk about various features as well as debug calculations and projects. Okay, so maybe we can start talking a little bit about the technical details. So we will focus extensively on the electron-phonon interactions, which govern a wide range of phenomena from transport to spin relaxation, superconductivity, polarons, and so on. So the simple picture is that the atoms are moving, and so they have displacements relative to their equilibrium positions, which I've noted as U. And these atomic motions perturb the periodic potential in the crystal. If you quantize the small atomic displacements and you express them as sum of normal modes, aka phonons, then this perturbation, which is shown here in red, gives rise to this linear electron-phonon coupling Hamiltonian. Basically, what this tells you is that as a result of the perturbation from the atomic motions, an electron initially in a certain electronic state in band N and crystal momentum K is scattered into a final state in a different band and different crystal momentum. And the scattering process is mediated by the absorption or emission of a phonon with a certain wave vector Q and mode index nu. The quantities that are central in the theory, which encode the scattering amplitudes for these processes, are shown in the left side in blue. These are essentially the coupling matrix elements in the theory. And if you look in the lower left, the electron-phonon coupling essentially include the wave function of the initial and final electronic states, as well as the change in potential due to the atomic motion written in the phonon basis. So I have expanded the expression here. Essentially, you have the periodic part of the change in potential from linear response DFT written in an atom basis and then transformed into a phonon basis. So the main innovation of the first principles way of computing these quantities is that now you can resolve the electron-phonon coupling matrix elements, which are basically the probability amplitudes for the scattering processes. You can resolve them for different electronic states and phonon modes, and that's something that was not possible in analytic models. So here I provide a reference to a short review on this formalism, and you can contrast that with the conventional theory of electron phonon, which is covered in book like Mahan's. Okay, now electron-phonon interactions can be both short-ranged and long-ranged. And so particularly in materials that have polar or ionic bonds, where the atoms could be viewed as carrying a net charge, the motion of the atoms generates long-range electron-phonon interactions. So typically, you can split the long-range parts into a dipole term and a quadrupole term, and everything else that is higher, like octupoles and so on, is essentially condensed into the short-range part. Now, the long-range dipole term is essentially what's known as the Frolic interaction. This is typically due to longitudinal optical longitudinal optical phonons. So when the two atoms oscillate against each other with an optical motion, that generates a long-range field, which is basically the field of a dipole. And if you Fourier transform that field just from electromagnetism, you realize that the electron-phonon coupling goes like the inverse of the phonon wave vector. So it goes like 1/q. Now, in practice, you can obtain an analytic expression where, however, the ingredients that enter, in particular the screening and the net charge in the atoms, is computed from first principles. And so this interaction can be computed from first principles. And in this older paper shown here on the left, we have shown how to include it in the first principles framework. And then you can compute transport properties such as the mobility in a polar semiconductor like gallium arsenide. And what this paper has shown is that you can predict both the macroscopic transport properties, such as the mobility, but also understand what is the mechanism that limits transport, which in this case is the emission of an allophonon in the conduction band of gallium arsenide. And we've also shown that you can predict the time scale for this process with a pretty stunning accuracy within a few % of experiments. So what really is unique about the first principles approach is that it gives you a microscopic insight into transport phenomena. A few years later, we're able to complete the theory and also include the quadruple interaction, which is a bit more subtle. It's present in ionic non-centrosymmetric, aka piezoelectric materials, like, for example, lead titanate or gallium nitride, as well as other nitrides. So here, the quadruple has a shorter range interaction, and therefore the coupling now goes like q to the 0. So it essentially approaches the center of the zone as a constant, and it's also non-analytic. Now, linear response DFT basically can capture both the short and the long range parts of the interaction. But the problem is that for the long range ones, you need to sample very small wave vectors because they extend out to very large lengths. And so the problem is you cannot access those very fine grids directly with linear response DFT. So the strategy is to first subtract these interactions and then adding them back after interpolating. But that will become clearer in the next couple of slides. Okay, now I wanted to show the workflow of how these calculations are done in practice. So using density functional theory, one can compute the electronic wave functions and band structure. And then using linear response DFT, aka density functional perturbation theory, or DFPT, we obtain both the phonons from the dynamical matrices as well as the change in the Kohn-Sham potential of DFT due to the atomic motion. And this can be done in principle for arbitrary phonon wave vector, but it's typically done on a regular grid. So the part of the density functional theory workflow is done with quantum espresso. Then there's an interface, which will be described in the code, that's called QE to PERT, where now these quantities are read in the Perturbo-code, and then we form the electron phonon matrix elements. Typical DFT and DFPT calculations are done on grids that are about 10K in Q points per direction. So in a bulk crystal, you could have for both the electrons and the phonons a grid that is the order of 10 by 10 by 10. The problem is that most observables of interest, both for transport, spin relaxation, and non-equilibrium dynamics, require very dense grids in momentum space, the order of 100 by 100 by 100 or denser grids, particularly for materials that have fine features in the Brillouin zone, such as steep bands or Dirac and wild cones and so on. So you cannot access those grids by brute force. And so the strategy is, starting from the coarse grid, you first project these quantities onto a localized basis set, typically 1E functions that are generated externally using the 1E90 code. And then on the coarse grid, you subtract any long-range interactions because you have their analytic form. Now, when you put this on this localized basis set, everything is short-range and decays rapidly, which means that by doing a double Fourier transform over the electron and phonon variables, you can interpolate it to arbitrarily dense grid. And then you can add any long-range interactions, which are inexpensive because you have their analytic expression. So now you have formed the entire electron-phonon coupling matrix element on dense grids, and that typically comprises billions or trillions of these matrix elements. So that's the most time-consuming step in the entire workflow. Now, once you have it using the Perturbo.x part of the package, then you can compute quantities of interest. And so we will focus on two main set of capabilities and topics or quantities of interest. The first one is transport properties such as the mobility, resistivity, magnetoresistance, relaxation times, and spin relaxation times. And then the second one is related to studying materials out of equilibrium as well as modeling ultra-fast spectroscopies. So I'm citing here some older papers from about a decade ago where doing these calculations, even for the simplest of materials like silicon, would require basically months of calculations. And now these things can be done, as you will see in this workshop, on your laptop within a few minutes. So this is a field where over the last decade, there has been enormous progress. And so that's why we're very excited to continue working on this problem, as well as hopefully attract new scholars to this area. So, okay, we'll start with topic number one, electronic transport calculations. One of the main properties that people are interested in computing when approaching code like ours is the conductivity, which is basically the proportionality coefficient between an applied electric field and the current in the linear regime, where the current is proportional to the electric field. If you're in a semiconductor, the intrinsic property is basically the conductivity divided by the charge density, which is the mobility. You can also add magnetic fields, and that's how actually most mobility measurements are done in practice. And so there you can be interested in how the longitudinal resistance changes with magnetic field. That's called longitudinal magnetoresistance. As well as the off-diagonal components of the conductivity tensor. So if you have a low crystal, if you have a low symmetry crystal, the off-diagonal components can be zero if you're not working along the main axis. But for them to be sizable, you need to break time reversal symmetry. And so with a magnetic field, you can basically have the classical Hall effect. And then people measure the Hall mobility, which is different from the drift mobility. And our code can predict both the drift and the Hall mobility. You can study these quantities as a function of temperature and doping. And really, one of the main scientific drivers is that you can understand what are the dominant scattering mechanisms and the time scales that govern these processes. And in cases where, for example, you have competing interactions, for example, between the electron-electron scattering, the electron-phonon, or electron defect scattering, you can basically understand which interaction is dominant in different regimes. Okay, so now I will cover the basic formalism, which will be described in more detail in one of the theory lectures this morning. So one of the main innovation from this entire enterprise of electron-phonon codes is basically computing the relaxation time for each electronic state. So early calculations that you could do with DFT, you would be able to access the band velocity. But then to compute the transport properties, you would need to assume some kind of a constant or energy-dependent relaxation times, which was either used as a fitting parameter or it was estimated based on some model. None of that anymore. When the electron-phonon coupling is weak, you can basically use Fermi's golden rule to compute the scattering rate, which is inverse of the relaxation time, and is shown here. And it's proportional to the imaginary part of the electron phonon self-energy. So from the point of view of many-body theory, what you're doing is you're computing this lowest order diagram, which is sometimes called the Fan-Migdal self-energy. So this gives you access to the state-dependent relaxation times, which basically gives the time scale for these scattering processes. So now scattering is only part of the story, because now you need to have kinetic equations to describe the electronic motion. And so the one that we will be focusing on in this workshop is the semi-classical Boltzmann transport equation, which basically works when the interactions are weak and you have well-defined quasi-particles so that you can ascribe an electron to a given electronic state and view it as a wave packet. Now, for transport, you're interested in a steady state where, for example, you applied an electric field and the electron distribution changes. So at steady state, the Boltzmann equation relates the change in the electronic distribution by virtue of applying an external force. So in the case where you have just an electric field, this is just the electric field E. And so if there were no collisions, then the occupations will continue changing in time and you will never reach a steady state. But basically the collisions counteract and ultimately establish a steady state. At low temperature, very low temperature, it's typically defects that are dominant, but over a very wide range of temperatures, say anywhere above 100 Kelvin or so, the electron-phonon interaction is dominant in most materials, except for materials where electronic correlations are strong, in which case the electron-electron interactions can also be important. And we will not discuss those in the workshop, but it's a topic that we're actually working on. So here, basically, if you keep the change in the occupations up to linear terms in the electric field, then the change delta Fk is proportional to this uppercase F. And that's basically the main unknown. So it tells you how much the occupation of each electronic state changes in response to the field. Then you can compute the current, which is basically given by this change in occupations relative to equilibrium times the band velocity, which you can compute from density functional theory. That essentially gives you the conductivity, which is a rank 2 tensor because it combines two different vectors, the applied electric field and the current, which need not be parallel in general. In practice, if you then substitute this form for delta F into the Boltzmann equation and you keep only terms linear in the electric field, in the lower left, this is what the Boltzmann transport equation, or BTE, becomes in practice. It's basically a self-consistent equation for this change in population F, where you have the first term, where F is just the product of the band velocity and the state-dependent relaxation time. That's called the relaxation time approximation. And so quite often you can stop at that, and it gives a pretty good account of the change in occupation. However, that does not capture backscattering, which is in the next term. And so if you want to include backscattering, then you can solve the entire equation iteratively. So typically, you start from an initial guess, which is just given by the RTA form for F, and then you plug that in the right-hand side and then continue solving until you reach convergence. Once you get there, you can compute the conductivity or the mobility if you just divide by the charge density as a function of temperature and doping. So the temperature dependence is mostly encoded in the relaxation time within the RTA or the change in occupation F. And there's also this thermal factor, basically how the equilibrium occupation changes with energy, that carries both the dependence on temperature and on the chemical potential, which is fixed in the calculation. Okay, so then using this framework, you can model anything from simple semiconductors, like I've discussed earlier, to far more complex materials. For example, on the right, I'm showing anthracene, which is an organic semiconductor with 50 atoms in the unit cell. Here, for example, in this paper, we have shown that it's the low frequency vibrations that primarily govern the mobility in this material. And you can also understand the temperature dependence and which specific modes are involved. But over the years, we've done these calculations on anything from complex oxides to simple and complex or topological metals. And in the current framework, you can also include defect scattering or study these processes for higher electric fields. And this can be done basically for, let's say, unit cells that are up to a few tens of atoms. And if you push it, you can get to about 100 atoms. In fact, the largest calculation we have done is for relatively high angle twisted bilayer graphene, where the system was about 120 atoms, I believe. So this leads to both precise predictions of mobility and transport properties, as well as a deeper understanding of transport mechanisms. So that was basically just the basics. And now I wanted to cover a few more advanced features that we've added in versions 2 and 3. In particular, in this sequence, I will talk about including enharmonic phonons, electronic correlations, and then modeling transport in magnetic fields, as well as spin-orbit coupling and spin relaxation. Other capabilities for transport include defect scattering and polarons, which are present in the code, but I will not discuss them today. So first, many systems have, softer bonds, so to speak, and or undergo structural phase transitions. A typical example is strontium titanate, which is cubic above 100 Kelvin, and it distorts to a lower symmetry structure at lower temperatures. But it's common for many other oxides and perovskites. So the problem is if you're interested in modeling the high temperature phase, and then you compute the phonons in density functional perturbation theory, it's going to give you some unstable modes. They technically have imaginary frequencies, which are shown here as negative. That's because the structure wants to distort to the low symmetry phase. And so those are the modes that drive that structural phase transition. Often these modes, which are also sometimes called soft phonons, are very important for transport and for other properties. So how do you model them? So back in 2018, we started interfacing our methods with techniques that have been developed in the field to model temperature-dependent, effective harmonic Hamiltonian. So you basically find at a finite temperature the best effective quadratic Hamiltonian that describes the phonons. So as you can see in this plot in the lower left, the method that was used here is called TDEP, and it gives you stable phonons that change as a function of temperature and also give very accurate phonons that very nicely agree with experiments. So now you can model all modes, including the soft ones. And so as we've shown here on the right, adding the soft modes in this material is very important to capture the temperature dependence, where you see the temperature dependence in experiment is temperature to the -3, which is nicely captured by the Boltzmann equation. The reason the mobility is overestimated in this material is because the electron-phonon coupling is stronger than is captured by the lowest order of perturbation theory. So you basically have large polarons. And so that's a problem that can be addressed with some techniques that we'll not discuss today. So starting with version 3, now we have interfaces in Perturbo with 3 different codes that are designed to treat enharmonic phonons. One of them is TDEP, the other one is SHA, and the third one is a la mode. And so basically, for these systems, one can compute the phonons using these methods and codes, and then import the phonons into Perturbo and basically compute the same observables, but with an accurate account of enharmonic phonons. Second, if you have materials with, and I'll put that in quotes, strong electronic correlations, in some cases, you're able to describe them in the framework of density functional theory with the Hubbard U correction. So these are systems that typically have partially filled D or F bands where the electrons are strongly localized. And the main driver to their electronic structure is the strong on-site electronic interaction, which is missed by plain semi-local density functional theory, which is a mean field method. So to compensate for that deficiency, in the DFT plus U technique, you can add a Hubbard-like term to the Kohn-Sham Hamiltonian. So that introduces an energy penalty for doubling occupying the localized D or F orbitals. And the energy scale for this on-site repulsion is given by this parameter U, which can either be assumed or it can also be computed from first principles with a linear response technique. So then you have an entirely first principle workflow to study some correlated materials, particularly insulators. And so here in this work, we have applied DFT plus U to a mud insulator, cobalt oxide. So in band theory, this will not be an insulator because of the electron count in the unit cell. What makes it an insulator is the strong local repulsion at the cobalt sites. So plain DFT predicts this to be a metal that is also unstable, as you can see in the lower left from the negative phonon frequencies. But now with DFT plus U and linear response DFT plus U, the phonons are predicted nicely, and the ground state is, in fact, an antiferromagnetic insulator. So, but we took this a step further, and we implemented electron-phonon coupling within linear response DFT plus U, where now the change in potential picks up an extra term. So in addition to the change in the Kohn-Sham potential, you have the change in the Hubbard U potential due to the atomic motions. So what we've shown in this work is that that term is as strong as the change in Kohn-Sham potential, and it's particularly important to capture both the long-range electron-phonon interactions as well as the interaction within the open D and F shells. And so now this gives us access to studying a wider range of correlated insulators. Just showing here an example. This is LCO, lanthanum copper oxide. This is also a mud insulator, and it's the parent phase for high-temperature cuprate superconductors, which turn superconductors when you dope them. Not much is known about the parent phase because it's difficult to describe, whereas the dope phase is a metal, so you can, to some extent, describe it in DFT. So with my former student, Benjamin Cheng, he did a very accurate DFT plus U calculation that correctly modeled both the band gap and the magnetic moment on copper. Very nice agreement with experiments. And then now you can study the electron-phonon coupling and resolve it for different phonon modes, which has shown that there's very strong coupling with different families of LO phonons, and that basically makes the spectral function for the electronic states very broad, and it's consistent with the spectral functions measured in experiments. And basically what this shows is that even the parent phase of the cuprate has an inherently strong electron-phonon coupling. This is just an example of things that you can study. Now, more briefly, for magnetotransport, you need to go back to the Boltzmann equation and add the magnetic field term, which basically gives you this extra term due to the Lorentz force. And now, remember that we're keeping things that are linear in the electric field. So now you can not just compute the gradient in K of F0 the electron distribution, you actually need to compute the gradient in K of the entire distribution F. So that needs to be implemented. And so that was a main challenge, where now this derivative in K, because you don't have rectangular grids in momentum space, they're still regular, but it's implemented as a centered finite difference type derivative. And if you do that, then now we can compute the entire conductivity tensor as a function of magnetic field. So that for the longitudinal direction, for example, XX, if the electric field points along X, you can model the change in resistance. But you can also access the Hall components, so the off-diagonal ones, and using those, you can model the Hall mobility. And so here, these are calculations that we've shown in this paper for silicon. And you can see that this method can generate, can predict both the mobility and the magnetoresistance in doped silicon in very nice agreement with experiments. There have been recent developments. In particular, we've also added the Berry curvature to this formalism, which enters through the anomalous velocity term. So now we can model magnetotransport in topological metals, as well as model higher order transport properties, such as the nonlinear Hall effect. And so we will have an archive on that this month. Anyway, the other class of materials that you'd like to model is the ones that have strong spin-orbit coupling. There's many out there, but in density functional theory, one way to address that is to basically include the spin-orbit coupling in the pseudopotential by using fully relativistic pseudopotentials that take the spin-orbit coupling into account at the atomic level. So now the wave function becomes a two-spinor, and the perturbation potential becomes a 2x2 matrix. And what was difficult to understand in the beginning is that the spinor needs to be rotated as a spinor, whereas if you don't treat it as such, this rotation has very large errors. And so in this paper, back in 2021, we have shown the correct way of doing it. Now with Perturbo, you can access the electron-phonon interactions in materials with spin-orbit coupling. Sometimes that's all you want, and then you can go on to study transport or other properties. But what we realized is that now you could use these quantities for a completely different purpose. In particular, if you have a centrosymmetric material, so that has inversion symmetry, the main mechanism for an electron spin to relax is that it gets scattered by a phonon, and at the same time, the spin flips. So when you have spin-orbit coupling, the electronic states are not purely spin up and purely spin down, but you can basically diagonalize as Z for the electronic state, and that gives you states that are nearly spin up and nearly spin down when a spin-orbit coupling is not exceedingly strong. And then you can access these spin flip matrix elements. Then you compute the scattering rate for the spin flip events and take thermal averages. And so that already back in 2020 has allowed us to start making predictions of spin relaxation times in semiconductors within this so-called LUDFA mechanism, so spin flip in centrosymmetric materials. So we've shown then that you can study not only spin relaxation times, but understand which phonons govern the spin relaxation process, as well as model the temperature dependence. We've made significant progress on this topic, more than I will cover in this talk or that we will cover in this workshop, but this basically opens to a wide range of applications in quantum materials and potentially quantum information science. So now, more briefly, I'll try to wrap up in 10 minutes probably. I will talk about non-equilibrium dynamics. So this is an inherently multi-scale problem where typically in experiments at time zero, you excite the material, typically with a light pulse, and that typically couples with the electrons. So you generate excited electrons, which then evolve on a femtosecond time scale. But then over longer times, the electrons lose energy to the lattice. So you create non-equilibrium distributions of phonons, which then evolve on a picosecond time scale because the phonon-phonon interactions are weaker than the electron-phonon interactions. So in Perturbo, you can start by obtaining accurate electron-phonon and in fact also phonon-phonon interactions. And so that, in a way, guarantees, and that's not a trivial point for non-equilibrium modeling, that you can trust the quantitative nature of your results. For example, you can trust the numerical value of the time scales as well as model ultra-fast spectroscopies and understand mechanisms in these ultra-fast processes. There's now, once you have the interactions, there's different kinetic equations that you could use for the non-equilibrium modeling. What Perturbo does is it uses what we call the real-time Boltzmann equation. It's basically you keep the time dependence in the Boltzmann equation and study how the populations of the electrons in the public version, but also we can model the coupled dynamics of phonons and also excitons and other quasi-particles. And basically, in the Boltzmann equation, this accounts for the incoherent part of the dynamics, which typically sets in about 5 to 10 femtoseconds after the excitation pulse. So you cannot model everything, and you cannot model especially the very short times, but it's extremely convenient to model the femtosecond to picosecond time scale that is often studied in experiments. There's various other schemes, obviously, from time-dependent density functional theory or Green's functions. Each one has its pros and cons and limitations. Like basically, the type of method you choose dictates the physics and the time scales that you can access. For example, in the Boltzmann equation, you can go out to tens or hundreds of picoseconds, and that's not possible in methods like time-dependent density functional theory or time-dependent GW. So we actually started this effort quite early. Back in 2017, we implemented the real-time BTE just for the electrons, where now you have that the electronic populations evolve according to the collision. So they usually excite the electrons and then lose energy to the phonons. But the phonons, you keep them fixed at the equilibrium temperature, and you evolve instead the electronic occupations. So if you look at this is basically a large set of coupled integral differential equations, because the right-hand side, which is called the collision integral, itself depends on the electronic occupations. And I have suppressed the band indices here, but this can be modeled for systems with multiple bands. So the way it works is at time zero, you basically excite the electrons into a distributions that follows the excitation pulse, and then you time step everything. And the way we implement it is we use the Runge-Kutta for time stepping as an algorithm with a typical time scale of about 1 to 5 femtoseconds. The phonons are kept fixed in equilibrium. But what made these calculations possible, particularly computing repeatedly at each time step and updating the collision integral, is that we have heavily parallelized these calculations. Initially with MPI plus OpenMP, and now also with GPUs. So typically, you work in a certain energy window, and then you find all the electronic K points of interest in this window, and then you find all the scattering processes that more or less conserve energy. Then you distribute those processes onto multiple MPI processes, and then locally you sum part of the collision integral just for those processes, and then you combine them to form the collision integral at each time step, and then time step the entire set of occupations. This is the method that's also described in Perturbo's paper, and that's publicly available. So things that you can do, for example, in this earlier work in gallium arsenide, we've initially excited electrons and holes with a certain distribution. And then what we found is that in this case, the hole carriers lose energy to the phonon significantly faster than the electrons. And we've shown in that paper that that has implications for the energy efficiency of gallium nitride light-emitting devices, particularly the problems of how electrons cool slowly and get emitted out of the device before they can recombine with the holes to emit light. So basically, you can use these tools for scientific discovery. In particular, recently we have also modeled the transient absorption. Now there's a whole set of tools inside Perturbo that you can use. We're starting from the time-dependent electron and hole populations. You can model a number of ultra-fast spectroscopies. Here, what's interesting is the plot in the center is an experiment from Giulio Cerullo's group in Milan on gallium nitride. And here we have modeled the change in absorption due to the excited electron and hole populations. You can do that using first principles optical transition dipoles from DFT or other methods. What's nice about it is that you can differentiate the contribution of the electrons and holes because you can access both separately. And so here, for example, the red line is our calculation that shows that the main trace in the experiment is due to the electron cooling. And so that's basically what really dominates the signal, and it's significantly slower than the hole cooling, which shows up at very early times. And so that basically confirms our prediction done using the real-time Boltzmann transport equation. In the interest of time, I will skip this one. So, okay, maybe something I should say again is you can validate the accuracy of the interactions by using the same electron-phonon interactions that go into your non-equilibrium simulation to compute transport. And so if the transport agrees with the experiment, then you're sure that you have a quantitative knob on this problem. You can also model non-equilibrium dynamics in strong electric fields. For example, that gives you a tool to access entire drift velocity versus field curve all the way to very high fields where the mobility typically saturates. So at low fields, you have the drift velocity grows linearly with the electric field, and the slope of that is the mobility. But actually, we can take this to very high field in a time-dependent way. And for each field, you reach a steady state, you compute the drift velocity. That allows you to trace entire velocity field curves. In this case, for silicon, as well as in other systems, as was shown, you can do it in very nice agreement with experiments. Tomorrow, the first talk will describe this effort in more details, but just very briefly, you can model the coupled non-equilibrium dynamics of electrons and phonons. This is significantly more difficult than just modeling the electron problem because the phonon-phonon interactions are more expensive to compute because of how one needs to use the entire Brillouin zone. Initially, we were modeling the entire set of integral differential equations where you're time-stepping both the electron and the phonon populations at once, but then with a very short time step that it's dictated by the electrons. So you can do things like you excite the electrons and holes, and then you follow in time, this is in graphene, how they initially generate out of equilibrium optical phonons in the middle panel. And then at longer time, you can follow up to about 100 picosecond how those excited phonons decay into lower energy phonons. And so reaching those very long time scales is complicated. This is very difficult, and initially we could only do it in 2D materials, but now in very recent work, we have interfaced this technique with the Sundial's library, which has state-of-the-art methods for time-stepping differential equations, and in particular, using adaptive and multi-rate techniques, we're now able to speed up these calculations by about 2 orders of magnitude with the same accuracy. Or stated differently, for a given computational effort, you can get 4 to 6 orders of magnitude better accuracy. Now, with this method, we can do not just 2D materials, but also bulk systems, which were previously just impossible to tackle. Just wanted to give you a flavor of what's beyond version 3 of Perturbo. In particular, our focus for future releases is going to be on capabilities to study quantum materials, as well as the machine learning/AI frontier to make these calculations faster or to generate entirely new workflows. So we've done extensive work on strong electron phonon interactions and polarons. And so some of those methods will find their way into future versions of Perturbo. For strongly correlated materials, this will be discussed later in the workshop, but now we can interface our methods not just with density functional theory plus U, but also with spectral functions computed from dynamical mean field theory. We can model spin dynamics in various ways, as well as magnon dynamics, so spin waves. And then finally, we're particularly excited by how tools that have been developed in the context of machine learning can be used to accelerate calculations of electronic as well as other interactions. So I will show just a single slide on this point. I basically told you that these calculations rely on billions or trillions of electron phonon matrix elements. As we started asking ourselves if this is an inherent complexity or if there's something that you can do to distill the main physics out of this problem. So we then started using singular value decomposition, which is basically a method to decompose rectangular matrices. It's decomposed into the product of two unitaries and a diagonal matrix, where the diagonal entries are real positive numbers that are called singular values. When the singular values decay rapidly, you can keep just a few of them, and that still gives a good approximation of the matrix. So this is used for images, for example, where you can see even if you keep 1 to 5% of the singular values, it still gives a fairly reasonable account of the image. So this method gives the best low-rank approximation of the matrix. How do you do it in the case of electron phonon interactions? That was the difficult part. And so in recent work, what we have proposed is that you take out all the long-range interactions and then you compress the electron phonon coupling in the 1A basis, effectively decoupling the electronic and the phonon degrees of freedom. The beauty of this is once you have decomposed the matrix this way, you can see that the singular values decay rapidly. But now obtaining the matrix elements on the dense grids in momentum space, which is really the bottleneck, has a cost that scales as the fraction of singular values. So if you keep only 1% of singular values, you obtain 100-fold speed up for the entire workflow. And the question is one of accuracy, but what we have found is that because of the effective compression and rapid decay of the singular values, pretty much all properties of interest in the physics of electron phonon interactions, from transport to spin relaxation, superconductivity, phase transitions, and so on, can be effectively compressed, where keeping only about 1 to 2% of singular values gives the same accuracy of the full calculation. And so in explicit timing test, we find that we consistently gain about a factor of 50 speed up in the entire workflow. And so this is a feature that will be added in future versions of the code, and I think it will make entirely new workflows possible. If you're curious, in recent work, we've also shown how to compress other interactions with more advanced machine learning frameworks. I'm quoting here a paper in the lower right that discusses that. So I think I went a little over time, and I apologize for that. As a summary, again, Perturbo is primarily a tool to carry out first principles calculations of electronic interactions, transport, spin relaxations, and ultrafast dynamics. What we like about it is that it's very user-friendly and efficient. It can, as you will see in this workshop, set up fairly easily, provides tools for post-processing and for learning, and for easily add new pieces of physics. We now have a wide user base, and so combined with our work and the work that's happening in the community, now this tool has made it possible to study a wide range of materials from simple to complex, particularly oxides, quantum systems, correlated materials, and so on. The new features, some of which will be described in the workshop, include GPU acceleration that make the code compatible with modern as well as future hardware, and a list of other features that I have discussed in my talk. Going beyond the current version 3, we're looking at adding methods to compress the interactions and significantly speed up their calculations. We have routines to compute coupled electron and phonon transport and ultrafast dynamics. So you can access the type of physics where you either drive the lattice out of equilibrium and study the lattice dynamics at longer times, as well as phonon drag in transport properties. And we're developing a wider array of tools to study correlated materials, as well as the coupling between excitons or magnons and phonons, and accessing completely different regimes which are governed by electron-electron as opposed to electron-phonon interactions. Okay, I think I should end here. And again, thank you all for being here. We're really excited and we're looking forward to the next 2 days of the workshop. Thanks.